All right, let's jump right into this explainer. Today, we are exploring the high-stakes, literal zero-margin world of engineering and installing massive, fixed steel offshore structures. We're going to trace the absolutely incredible journey these giants take, right from the drawing board all the way down to the bottom of the ocean.
So think about this for a second. Building an offshore platform, it is nothing like constructing a skyscraper on land. There's no foundation to pour. And crucially, there's absolutely no way to just drive back and easily fix a mistake once you're 200 kilometers offshore, floating in 150 meters of violent ocean water. Every single thing has to be done flawlessly, the very first time.
Now, when we look at one of these platforms, we usually just see the top deck, right? The living quarters, the processing modules, but beneath the waves lies the true intricate anatomy of the platform. The vast majority of the engineering genius is completely submerged, completely out of sight. Just look at that crazy web of diagonal cross bracings, the conductor guides, and those massive legs extending all the way down to the seabed.
That submerged, heavy-duty workhorse, we call that the jacket. And it's exactly what pins the entire operation securely to the seabed. It's actually been the industry standard for over 70 years, mostly because, well, it's simple in concept but incredibly robust. These jackets are built from individual cylindrical sections of rolled steel, we call them cans, and they're welded together into this massive three-dimensional lattice.
Now, I really want to highlight the nodes. These are the heart of the structure's integrity. Basically, they're the complex joints where those diagonal bracings meet the main legs. And let me tell you, they are among the most highly stressed intersections in any structural engineering project on Earth. They require absolutely flawless, full penetration welds. Why? Well, because these specific points have to survive decades of violent, continuous cyclic wave fatigue. Seriously, one bad weld at a node and the ocean will eventually just tear the whole platform apart.
So everything starts in the engineering office, long before a single piece of steel is even cut. Engineers use advanced finite element analysis, or FEA software, to guarantee the structure can survive the absolute worst conditions imaginable. And they don't just guess here. They model the structure's response to thousands of different wave load conditions. The ultimate benchmark? Surviving what's called the 100-year return storm. That's the single most violent, massive storm statistically expected to hit only once in an entire century. The structure has to carry the crushing weight of the topside modules while resisting aggressive winds, relentless currents, and towering waves.
Okay, so how do we actually build this thing? Well, fabrication begins in specialist yards, usually in places like South Korea, the UAE, Malaysia, or Indonesia. Massive steel plates are rolled into those cylindrical cans we mentioned, then welded end-to-end to form massive tubes, and finally assembled at the nodes with incredibly strict temperature controls. And to make handling all this heavy steel a bit easier, whole sides of the jacket are actually built lying flat on the ground. Then, using these massive synchronized cranes, they carefully roll up the horizontal frames into a vertical position.
And remember, because you literally can't just patch a critical weld once it's hundreds of feet underwater, every single joint undergoes an extreme battery of non-destructive testing before it ever leaves the yard. We're talking ultrasonic testing, magnetic particle inspection, and radiographic testing, basically X-rays for steel. They use full penetration welds, meaning the weld material must completely fill the entire thickness of the tube wall, applied in multiple passes. Like we said earlier, there is absolutely zero margin for error here.
To really grasp the sheer scale we are talking about here, we have to look at the numbers. While a small shallow water platform might only weigh a few thousand tons, a large deepwater jacket designed for, say, the central North Sea, that can weigh up to an astonishing 30,000 tons. Let that sink in. That is the weight of dozens of fully loaded jumbo jets made entirely of welded steel tubing.
To put that massive scale into perspective, just look at this towering yellow steel lattice. This is a sea harvester-style jacket waiting for transport, and it completely literally dwarfs the heavy dockside cranes and the yard workers standing around it. Honestly, just moving something this unwieldy out of a fabrication yard and onto a boat is an immense engineering challenge in its own right.
In fact, the loadout, moving the horizontal jacket from the yard onto the transport barge, is actually one of the highest risk operations in the entire process. Sometimes the jacket is skidded out onto the barge over grease-coated rails. But other times, they use linked fleets of self-propelled modular transporters, or SPMTs. These things are wild. They're hydraulically steered flatbed trailers with hundreds of tiny wheels. A single unit might carry 50 to 100 tons, but you link dozens of them together and they can carry up to 30,000 tons, maneuvering this colossal structure with literal centimeter precision. Once it's finally on the barge, it gets secured tightly with massive welded steel C-fastenings.
Now, before the days-long or sometimes even weeks-long ocean tow begins, everything must be perfect.
independent marine warranty surveyors step in to rigorously inspect those sea fastenings holding the structure to the barge. And you know, insurance companies absolutely require this because you are about to take a multi-million-dollar, incredibly top-heavy steel skyscraper and drag it through rough ocean swells.
So once we finally arrive at the offshore site, we reach the real moment of truth, getting it into the water. And this is tackled in two entirely different ways depending on water depth. For shallow to medium water, we use a crane lift. It's a clean, controlled, vertical placement using heavy lift vessels. But for massive deepwater jackets, they perform a barge launch. Basically, they horizontally slide the whole thing right off a tilted barge and upright it using controlled flooding.
You can really see the stark difference in approaches right here. On one side, we have the incredibly dramatic deep water launch. The barge is intentionally tilted, and the massive steel structure essentially crashes into the sea on sliding rails. On the other side, you see the delicate, super precise crane lift, where the structure is hoisted vertically by specialized heavy lift vessels equipped with cranes capable of lifting up to 14,000 tons.
For those deep water launches, the sequence is frankly a true engineering ballet. After the jacket violently slides off the barge, years of mathematical calculation are put to the test in a matter of seconds. As it enters the water, the structure actually uses its own geometry and natural buoyancy to begin uprighting itself. Then, through a series of carefully timed, remotely controlled valves, specific compartments inside the legs are flooded. This causes the giant structure to gracefully rotate into a perfectly vertical position, just bobbing there in the water.
Okay, so now it's vertical and tugboats have maneuvered it to the exact target location. But it's still just sitting there floating. To finally secure it to the seabed, we use piles. For smaller rigs, these steel piles are driven directly down through the hollow jacket legs themselves. But massive deep-water rigs are simply too big for that, so they require the large, heavy-duty external pile clusters attached right to the base of the legs.
I like to think of these piles as 50-meter-long steel tent pegs. They are driven into the ocean floor by massive hydraulic hammers that strike with the sheer energy of a small bomb. They force these steel tubes anywhere from 30 to 90 meters deep into the subsea soil. Then, to permanently lock the whole thing together, the annulus space, that's the gap between the pile and the jacket leg, is pumped completely full of cement grout. Meanwhile, large steel grids called mud mats sit directly on the seafloor, distributing the platform's incredible weight so the whole structure doesn't just sink into the mud. So the next time you flick a light switch or start your car, take a second to think about the journey of these structures. From those intense FEA computer models to the flawless full penetration welds, right down to a 30,000-ton steel skyscraper gracefully sliding off a barge into 150 meters of freezing ocean water. Extreme effort, immense danger, and pure engineering genius happen entirely out of sight, beneath the waves, just to fuel our world. I want to leave you with this thought. Does knowing the staggering, hidden engineering happening beneath the surface change how you view the energy powering your everyday life? Thanks for joining me for this explainer, and keep your curiosity switched on.